All right. We are live. Hello, Nicholas. Welcome back. Been a couple of weeks. How have you been? I mean, it's been a couple of weeks of no stream. As always, let me know if sound should be adapted or background music, any of that. Let me know if anything's not loud enough, too loud, whatever. All right. So I'll grab our profiling data for today. Hello, Matthias. Glad you're joining. Music is perfect. All right, thank you. Just pulling up our profiling data for today, and then we can get started. So, just in case, you want to follow along, or you want to have a look at the profiling data yourself, I'll paste the link to the profiling data in chat. You can obviously choose to follow along yourself, or just watch the recording or whatever. We've often had people check out the profiling data and make suggestions of what to check out. We can definitely do that, but without further ado, let me switch over. So today is going to be kind of part 2 or 3, depending on how you take it, of optimizing the Kubernetes Kubelet. So what we're looking at right now is a snapshot of some profiling data from one of our production Kubernetes clusters. This is a Google Container Engine GKE cluster, version 127. And we used pretty much exactly the same. I took this snapshot only a couple of hours ago, but we'll quickly check out the code path that we optimized last time, and then we can try to search for our victim for today. Quick reminder, let's dive in. What we were looking at last time was somewhere in here. It was something cAdvisor specific. And actually, let me just search for it because I remember it. There was some regex stuff going on. Exactly, it was this must compile, and then there was this splitting going on. And basically, if we remember back, Google cAdvisor. It was actually merged since last time. If we remember, we optimized, close to 100% of this code path away. So it actually should materialize in something like 1.5% of the baseline CPU usage of the kubelet going away, potentially even more. What's hard to gauge is the amount of garbage collection that we saved. We definitely did save a bunch of garbage collection as well, so maybe, you know, it could be even more than this, but we won't speculate too much about that. But you know, there's definitely some amount. But the 1.5% we can be pretty sure about. So that's pretty awesome. So we can kind of ignore this code path today, but there were already a couple of other code paths that were fairly obvious to us when we were looking at it last time. So one of those was everything that had to do with reading integers from C groups. In case you're not familiar, what CAdvisor does in the Kubernetes Kubelet is it kind of monitors the resource usage of containers to then be exposed for as like Prometheus metrics, for example. But they're actually also internally used by the kubelet. So it's not just about metrics and monitoring. It's also about you know, the kubelet fundamentally doing some work. So this is a pretty core thing that the Kubernetes kubelet needs to do. And the way that the C groups in Linux work is that the limits, and I want to say also the current usage, but I'm not 100% sure about this one. I would need to look at the docs myself. Are in a special virtual file system called cgroupfs, and there are various files that you know, are named, and then there's just a number in this file, and basically everything that CAdvisor does is find all of these files, read them and parse them, and then expose them, or you know, use them further. Music is a tad too loud for me now. Okay, yeah, no problem. We can fix that. I'll turn it down a tad. That may just be that, you know, maybe the next track came on. I think I turned it down in OBS. If it's not better, let me know. Yeah. We can continue to adjust. All right. So yeah, hopefully that kind of explains a little bit about CAdvisor and what it does. But as always, feel free to write as much as you want in the comments. If there's any code path that you want me to check out, or if you have any suggestions for the code. Last time there were tons of amazing suggestions. It was almost like we were pairing on like a video call. That was pretty awesome. I like that a lot. So feel free to interact as much as you want in chat. So one of the code paths, and maybe this is the one that we can explore further today, was about reading these integers from files. So it was something like read UN64, if I remember correctly. Yeah, here. That's exactly the one that I'm talking about. So it looks like, I mean, we can dig deeper into this. And let's actually, well, that's pretty large when zoomed in, maybe not. We can see that this basically calls this, the read UN64 function calls the read string function, which then just calls out to os.readFile, which of course has to allocate a slice. This is something that definitely should go away. This is somewhat surprising to me that closing is so expensive here. I wonder what this is about. Open at. So I think if we basically replace this with a much more scoped version of reading files that doesn't use read file, that allocates exactly the kind of slice that we need, I think we'll do much better with this. So all right, let's get started, and we'll start with writing a benchmark where we're benchmarking the current approach, and then we'll try to optimize it, and we'll see if we can improve it. As always, this is totally unscripted. I haven't tried this. I have no idea if we're gonna make anything better. Maybe we'll make something worse. That's kind of the fun of this format. We never really know what's gonna happen. So yeah, let's give this a try, I would say. All right, so last time I remember we pretty quickly needed to go onto a Linux machine. I typically develop on OS X, so I'm just gonna SSH into my little server here. So here we still have our profiling data from last time. We'll just remove that. And our profiling data was suggesting, what's going on here? We should look at the common package read UN64. Okay, so common. Oh. It's container common. Container common. Oops. And I think it said helpers.go. Okay. Okay, looks like we already opened this file at some point, probably in the last episode. So we can jump into this read UN64. Let's read what we're doing here. So we're reading this file, or we're calling this read string function. Okay. This is an interesting one. So there are cases where maybe we're being returned not numbers, but a literal called, or that is max. That's good to know. And then basically we just, whatever we get back from this read string function, which we'll have a look at in a second, we are going to read an unsigned integer from that is base 10, and we'll read it to be, we'll read 64 bits for it, which is exactly what we, what I would have expected from this function. All right. So let's have a look at read string. So it joins the directory with the file, that's fine. and then called read file. That's fine. And it trims the space. So I'm actually surprised we're not seeing this in the profiling data, because this returns a byte slice. We then turn the byte slice into a string, which creates a copy, and then we trim space, which potentially again creates a copy. Let's have a look. I forget exactly if it does. Okay, cool. No, this doesn't create a copy. That's good. It only returns the subslice. That's good, but let's maybe have a quick look if we can see this allocation that should be happening here in our profiling data as well. So we have read string make slice. Interesting. We'll see if it shows up in the profile in the benchmarks. Okay, so I think what we're gonna start with is we're gonna replace this read string with a more optimized function, because something that we've seen a couple of times in the past, this stat call ends up being pretty expensive, and the only reason why we're doing this stat call is to figure out the size of this file, which we then allocate all at once to then ultimately read all of this data from. And in our case, we don't actually need to do this because all that we're doing is something much more narrow, which is we're reading a single unsigned integer from a file, so we can know exactly how much how many digits there are going to be. So we're gonna create, first let's create a benchmark. Maybe we already have a benchmark, I don't know. Benchmark. Okay. This is actually interesting. So there's a parse UN64 string, but it's not used in that function. What is going on? Okay, weird. I would have deduplicated, but that's all right. It's probably, you know, historically grown software. It happens. We all miss things. But looks like we don't have a benchmark for this yet, so we're going to create one. Benchmark read UN64. I wonder if there's maybe list resources. Oh yeah, nice. Okay, great. This is actually going to be super useful. Because we're going to be able to use all of this. Awesome. Actually, of course. I would say let's just grab all our files, and we file path dot walk test. What did we call it? Test resources. Copilot is once again getting ahead of us. So I don't think we want that. We want to check the error first. If n is nil, we return our error. And if info is here, I believe is the function. If it's not a directory, but we add it to our files, correct? And then we return no error. And what do they use as cert? All right. So before we do anything else, let's give this a try. We'll use our cool trick as always, so we don't run any of the tests and we just run our benchmark, which we call this. Oh, I actually wanted to print them. Okay. All right, cool. So now for each file, we create a sub benchmark. Want to make sure we don't optimize this away, and for some reason this had this. Oh, that's the tab. Ah. Oh, not a huge fan of this API, to be honest. I guess we could do this. I'm not sure I like that a lot. We'll just give that a try for a start. Yeah, we'll ignore a couple of files. That's whenever we have any CPU sets. Still print? No. Oh. What was that? What just happened? Okay, I don't know what that was. We are going to ignore anything. Oops, what happened? Well, My NeoVim just completely froze. What is going on? Wow. Why can I move my cursor but not? I think something very strange is going on. I think this must be some alacrity thing. I don't really understand. Oh, wait, what? No. Huh? No. Okay. Alright, I'm gonna restart my terminal. That does not happen. That hasn't. I don't know if that has ever happened to me. As always, let me know. If the font size is fine. Wow, I'm blown away. I don't know what just happened. I did anyway. Oh, where did it put this one? Hello, Jimmy. Welcome on the stream. Yeah, the thing is, this is on like my Linux server because we're editing some like C-Advisor stuff. This is not my typical NeoVim configuration, so I'm struggling a little bit right now to actually maybe our other NeoVim is actually still running. Yeah. Maybe. I'm hoping that cleaned itself up. No. All right. Local state swap. Okay. Okay. We are going to ignore contains CPU set. That was the one that was behaving in ways that we didn't like. What? Does not contain CPU set. Okay, starting to look better. Okay, what's this? Contains two numbers. CPU max. What is that? What is that? is that happening? Everything is fine until some point. Let's we'll try to be quick this time to cancel whatever is happening. Memory, PID, secret v2, PID, CPU wait, memory, swap, PIDs. What is this? Yes, I love this CPU. Fun fact, what I now use as my Linux server is what I started Polar Signals on. That was the perhaps it's easier to append to files only when read-uint succeeds. Interesting. So I think I like that suggestion, but this thing doesn't actually return an error, which I probably would have done differently if I designed this API, but I don't think I want to change everything in CAdvisor that calls this function. I would prefer if we can just swap it out at the end for a better version of this function. It was something C group v2. Yeah, you're right. That does look like JSON. Oh, you are totally right, of course. You are absolutely right. Thanks for catching that. Well, let's ignore that. So hopefully now we have all of our, and let's nice. We had some coffee talk in chat today as well. Love to see that. All right, so we've got our base benchmark. So I think at this point we can already clearly I need some coffee today. We can already commit this. So what was it? Containers, container or containers? Container, common, add benchmark for read u int 64. All right, so we've got that. We've got our base now, so we can try to improve this. So we can read n bytes from file, and we just have a file path, and we say n, and I would prefer to I guess we'll follow what they do in the library. I don't particularly like it, but we'll stick with it. So, well, maybe n is the wrong. So, got a comment in chat. Spent more time than I care to admit looking at escape JSON. Yeah, I know the feeling. So, we can use that, and the nice thing is, you know, we can, because we know that this is always a uint64, we can figure out exactly how many digits there are, and we can, you know, just count. I happen to actually know the number of digits in the max uint64, but for the sake of this, we'll count it real quick. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Exactly, it's 20 digits. So what we can do is we'll do full path is path that running here in file, and then we'll do out is fine. I know we said we want to follow what they do, in which case let's read string of the function. So on an error, it does this. Jimmy is asking, how was PromCon, by the way? I get FOMO every year. It was super awesome. Fun fact, Polar Signals was actually organizing PromCon this year, which was an honor, and, you know, sort of a homecoming for us, not just because we come from the Prometheus community, but it was also organized in Berlin, which is not only, you know, where we live, but also where Prometheus was originally created. So that was super cool. Probably we'll see in a second, but I expect that we'll probably see an EOF error here because we're reading the whole file. So hold on a sec. I think read is allowed to not return. Yeah, it only reads up to B bytes. We actually need to do something additional. It's like read full or something like that. Going read full. Not this one. Read all, read full. Yeah, here we go. It's io.readfull. And it returns, and yes. And here we can do the same thing, but check if it is error equals what? All right. Now we can remove this comment, and now we can actually use this by using read and byte from file whole path. I'm going to remove this. Now we get a byte slice back. So we need to do bytes dot equal. Part of the whole point of why we wanted to do this is to remove allocations. So, and here we can use 0. Now we are going to write a custom function for parsing this. It's actually fairly easy to do. So we'll do parse base 10 UN64. And we'll have our buffer, and it's that. What? Do we have this already? Parse base 10. Oh, I don't know. GitHub Copilot seems to be hallucinating today. So we want to iterate over each position, and we create a result, which is a UN64. That, and now we do yes, that exactly. This ensures that we actually have an ASCII character that is between 0 and 9, and then we take that ASCII character like code point, and we have subtract 0, and length of buffer minus I think we can do this a little bit simpler. Yeah, we're like anything open source, you know, it doesn't, I don't think we're very worried about that, but good question to me. I guess we can leave this for now, and we can check if the profiling data suggests that we should optimize this. So use that. I guess we could instead here. Yeah, that. Then we replace that with car space 10 with 4 out. Now let's see. Let's see if this is not right. We return nil here. We don't need to add anything here. So now. Yes. They did trim space. Do that here. Byte trim space. Fail to read unexpected EOF. So let's the read. What's happening here? It's unexpected EOF. That's okay. Because we're telling it to read 20 bytes, even though there may not be 20 bytes then. So exactly this. And if I'm not totally mistaken, I think we can already see an improvement here, but we'll use our typical bench stat to compare. And if I remember correctly from last time, I should really fix this. I don't think bench stat, the slash bin is in our in our path, so we'll call it like this. All right, so okay, so the geomean says we have gotten about 15% faster. We'll take that. That definitely means, you know, what did we start out with? It's not super huge, but of, you know, almost 3%. That means we optimized maybe maybe half a core, sorry, no, half a percent or something like that. That's pretty good. Not too bad for less than an hour. But I do wonder that let's increase this, and let's see if there is something else. Oh, thanks, Matthias. Now you can see it though over here. We're about 15% faster. I'm just rerunning now so that we are going to get some profiling data from this so that we can see, if there's anything still very low-hanging fruit that we can optimize here in our implementation. But 15% is already not bad. Right, should be almost done. We're being pretty extensive today with our benchmarks. All right, so let's run that one more time. Okay, we're still in a similar region. Sorry about that, you couldn't see that, but we're still in a similar region. So we now have some profiling data, so we can use our nifty tool to upload this. Yeah, we don't have a... Okay, so interesting that file close is so expensive. So it looks like the only thing that we could potentially still do better is path.join, but it's a shame. It is a shame that this is the architecture of this thing. But I don't think we can change anything about that at this point here. So, and I mean, it would be another 5%. I wonder if there's something that we could do. But it seems like 1% is spent in creating that slice. %, converting the byte slice to a string, and half of that in cleaning the path. I think this is probably as optimized as we can make it at this point, but we'll take it, it's another half a percentage point shaved off of the kubelet. So we'll commit this. Container common replace read kubelet or with optimized version. This patch replaces the read to N64 with one that optimizes reading to N64's files only. It prevents unnecessary calls to that, because a valid UN64 can be 20 characters at most anyway. It also avoids the allocations. Overall, benchmarking has shown to reduce the total CPU time by 15%, which, given a total usage of roughly 3% in the entire kubelet, this means we're reducing the kubelet baseline CPU by about, what's 15% of 3%? So of course it would be 0.3, so roughly 0.45%. Did I already set up an origin here? Yes, I did. I committed to master. I don't know if I like that. Let me create a grind for this. Read you for. Alright. So. Profiling data from the kubelet, filter it down to only show read 4. Here. Someone opens this link, they will see this. All right. Oops. Should have edited the title. Oh. All right. So, we've only spent about an hour. I don't think we will have enough time to actually finish another optimization. But I think what we can do is we can already start to look a little bit at the profiling data, maybe look a little bit at the code, and then continue our investigation next time. So back to the drawing board. So the next thing that seemed somewhat obvious to us last time was there was a code path that was involving Prometheus metric collection that kept allocating descriptions over and over and over and over again for some sort of metric collector. I forget exactly what it was, but I want to say it must have been somewhere here. It is still the advisor. So it's the metrics.prometheus collector collect container info. And yeah, exactly. This is the call that we were seeing. We can see that just calling new description over and over and over and over and over again is using 1% of our CPU usage, and it feels like we should be able to optimize this away quite well. But let's have a quick look at what this stuff does, because this is obviously a bigger, looks like it's bigger than these things individually. Get requested containers info, get info, update subcontainers. Let's first dig deeper into this. Get spec internal. Ah, look what we just found. And get internal spec calls. This actually looks like the inlining information might be incorrect, but let's have a look. Let's have a quick look at get spec internal. I'm guessing it's also in here. Yeah, get spec internal. Oh no, it actually does call that. I suppose it does that to check if the file exists. Checks creation time. So it actually wants the mod time. So it's not really about it's not about figuring out if the file exists. We actually want to understand when it was created. Okay. Okay. Then it checks if it has the various directories for C groups. What else was happening here? Read string. Let's see why read string is called here. This is the CPU set that we see. We had some example files for this. So we've got another one. I just want to have a look at those as well. That's something that we already looked at. Get that into something new. Okay. CPU set.cpus. What's that? Maybe it's not filter. Okay. It seems like that should also be similar. Maybe we can check what. So read string in total uses about 3% of the kubelet's CPU time. And it looks like get spec internal is the code path that does that. Yeah, I think every single one here leads to get spec internal. Yeah. Okay, interesting. But read string is also happening in the read UN64. So let's compare that. So we had almost 3% there already. So it looks like, you know, there's not going to be a whole lot that we're going to get out of optimizing that. It's probably, you know, in the long run still worth it, but maybe not the biggest fish we can fry right now. And I think all of this, yeah, all of this is just pretty much doing the same thing. All right. I think this is the thing that just bothers me. I want to understand what's going on here. Let's have a look at this file. Sorry, this one. $1,814. 1,000. So, I guess this probably changed since. So we call new description specifically. If I remember this correctly, last time there were a whole lot of different call places where this was happening. So maybe we can start with this function. So we get all of our labels. This returns a map. Okay. So ultimately, all this does is we iterate over the label names. Then we have a set that contains all the label names. And now we iterate. Okay. We probably do this because Prometheus wants the defined labels to be consistent across all series. Technically, this is not part of the specification of the Prometheus format, but it makes a bunch of things on the server side a whole lot more optimized. Whew. Oh, tired. So we try to adhere to this. Okay, so we duplicate faults. Okay, so we just try to deduplicate because we could theoretically sanitized label and we iterate over the label. What's labels again? Created here. Okay, so we append to it if we haven't already seen this label. And container labels, if we append to the values, how can we? Okay, we end up creating two slices that are always label name, label value. And so at position 0 of label name, we also have the label value in the other slice. Okay, that kind of makes sense. And we do this for each label, and potentially we just append an empty label value, which Prometheus would just discard. Okay, so then we create the description for every unique label set. And we do this on every iteration to know, to be sure that we always have the correct label set, even if the labels may have changed for this container. So while this is definitely correct, I think what we can do is we can create all of these descriptions for the label sets, for the label names, and as long as the label names don't change, okay, this is going to be a tough one to benchmark. Container start time seconds, is that one of those that we then set there? Yes, container start time seconds. Okay, so I think that is going to work. We basically check, we outside like in this collector, we store some state where we keep the descriptions, and we keep a key basically that says what these descriptions were valid for. And if the key doesn't change, then we don't have to recreate descriptions. We can just use the ones from the previous iteration. Now, Prometheus, potentially we need to make sure that there can't be a data race here, so we would need to protect this with a mutex. But yeah, I think that should work. But this is something that I definitely would want to benchmark. So I wonder what we can do about that. Okay, so this is all mocked, basically. Maybe there are already benchmarks for this. Metric, Prometheus, test collector, yeah, any benchmark. No. But there are some tests, so let's have a look if we can just copy this basically. Benchmark, Prometheus collector. Just doing this so I don't have to rewrite their testing framework here. Registry is our gatherer. Now let's see. Oh. Oops. Yes. Benchmark this thing. Maybe 1,000 is too many. And I want to see profiling data. I feel like this is maybe a tad too fast for the profiling data that we were seeing. But let's have a look. So it looks like this benchmark did not at all exercise the path that we wanted. Let's make sure we read the rest of the code actually. What was the code path? Collect containers info. So we collect start time, CPU period, CPU quota, CPU shares, memory limit, swap limit, reservations limit, new metric with timestamp, yeah, okay. That's not a call to new description. So we do here. C labels, raw labels plus metric labels. What are metric labels? Okay, I think okay, the function also ends here. I think it's all the included metrics here. Get values. Okay. Here, extra labels. Okay. Okay. So this is a way for them to add new labels to this stuff, which makes it a little bit more complicated, but it's doable. Although, what do I see there? Labels. Oh my. I know that's the label values. Thank God. This is the label names. This is the label values. That is okay. We can live with that. Anything else use these? Use the additional extra value here. Task state, okay. Makes sense. Okay, looks like quite a few use them. Still, actually, this doesn't change anything because these labels are not dynamic. The whole problem is whenever we keep creating descriptions with label values and label names that have appeared or disappeared. So this doesn't actually matter because these are all hard-coded. The only thing we care about are the dynamic ones. That's very good. So that should mean, and I think we're a little bit too far into this episode to actually implement this, but this is where we would, and we are going to pick up next time. We'll basically create a key for each unique set of label names that we see. We store that in the struct, and then on the next iteration, and we create all the descriptions, and then if nothing changes, we just reuse those descriptions. But if something does change, we recreate the descriptions with the new label sets. And therefore we can continue to be, a nice citizen in the Prometheus ecosystem, but we can also prevent these new descriptions from being recreated over and over and over and over again for, you know, not really any value. We don't absolutely have to recreate them. We only have to recreate them when the labels actually change. So, you know, I think we didn't make too much of an impact today, but 0.5% is 0.5%. We you know, we still made some improvement. So yeah, thanks everyone for joining. Thank you for the amazing lively chat today. Hopefully see you next time. Do please leave a subscribe and a like on the video. It helps us gauge you know, all of your interest. And then next time I think we're going to be seeing a bigger improvement again. So until then, happy profiling and see you all next time. Thanks everyone for stopping by.